Hello viewers, welcome you all. In this lecture, I am going to take up the questions related to the topics that I have covered in the previous lecture, right? In the previous lecture, I have covered two topics. The one was semi-empirical mass formula of the atomic nucleus, and the second was nuclear shell model, right? I have discussed both these topics in details, and I have explained that which kind of questions are asked in different competitive exams related to these two topics. So today in this lecture, I am going to take up some questions related to these two topics, right? So I am going to start with the questions asked in the GATE exam. You can see here, I have opened the questions of the GATE exam. The question is, in the nuclear shell model, the spin parity of 7 nitrogen 15 is given by. The nuclei given is a 7 nitrogen 15. So first of all, we know very well that we have to write the number of protons and number of neutrons. So proton is equal to 7 and neutrons is equal to 8. So it means this nucleus has a unpaired proton, right? So we have to write the configuration, right, for the protons 7 number of protons 7, right? So we know very well what is the configuration and how we write it. It is 1s 1p 1d 2s. This is the sequence. So we'll start with 1s 1 by 2. It is written here, but they have taken different way of solving it. So 1s 1 by 2 to 1p 3 by 2 4, and the last one is then it will go 1p 1 by 2, right, 1, right, 4 plus 2 6 plus 1 7. So this is the last cell in which the proton is present, and for this it is 1p 1 by 2. It means J is equal to 1 by 2. So spin is equal to 1 by 2. It is given here. For P, L is equal to 1, it is written here. So parity is equal to minus 1 power L. So it is negative. So spin and parity of this nucleus is 1 by 2 negative. So this is the way, very simple question, but it is simple only when you know the structure of the configuration of the nucleons. Only then it is possible. If we don't remember that sequence, then the thing will become very difficult, right? So this was the first question. Now I am going to the second question. In GATE exam, mostly the questions are asked from the shell model, and they are related to the spin and parity. Now the question is, the semi-empirical mass formula for winding energy of nucleon contains a surface correction term, right? This term depends upon the mass number. We know very well that B surface energy term is equal to A surface energy into A power 2 by 3. Right, this was the term that I told you in that lecture. So you can see here, C is the correct answer, right? B surface energy directly proportional to A power 2 by 3, right? And why this term was arising, right? This term was arising because we have overestimated the winding energy in the volume energy term, right? It is also negative. I have not considered here sign negative because it is reducing the stability of the nucleus, right? This is a very simple question related to the semi-empirical mass formula, right? Or we also call it as a CF von Weizsäcker formula, right? Now the next question is again from the shell model. According to single particle nuclear shell model, same thing, don't confuse in it. The spin parity of the ground state of 8 oxygen 16. 17. 8 oxygen 17. So protons 8, neutron 17 minus 8, 9, right? So in this case, now it is a case of even odd, right? And the earlier was the case of this was the case of odd even nuclei. So we know very well for odd even or odd even nuclei, the spin is because of the last nucleon that enter in the given cell. So in this case, the unpaired or last nucleon is a neutron, and it has a number 9. So we have to write down the configuration up to 9. So again same sequence, 1s 1p 1d 1s 1p 1d 2s. I think I will write 1s 1 by 2 power 2, right? 1p 3 by 2 power 4, then 1p 1 by 2 power 2, 4 plus 2 6 plus 2 8, then 1s 1p and then 1d 5 by power 1. So this is a sequence 1s 1p 1d 2s. So 1d 5 by 2. Then after we will get after 1d we will get 2s 1 by 2. This is very important. Then 1d 3 by 2, right? 2 and 4. So our configuration is up to this point. It means the last nucleon is going into the cell 1d and 5 by 2. So J is equal to 5 by 2. Very simple. You can see here, right? The spin is equal to 5 by 2, and for D, L is equal to 2. So parity is equal to minus 1 power L. So it is positive. So spin parity is equal to this, right? This is, we have to remember one thing always, that whatever spin and parity we are calculating in the cell model, all these are related to the ground state of nuclei, right? If we talk about the excited states, then we have some additional formulas for that, and in some cases the cell model doesn't correctly predict the spin and parity of different nuclei in the excited states, right? But mostly the question are asked from the ground state, right? So this was the next question. Now I am coming to the next question. You can see here. The question is again, the nuclear shell model. In the nuclear shell model, the potential is modeled as, right? This one is given, right? The correct spin parity of and isospin assignment of the ground state, right? This one. Now we don't have to look at the potential. We know in case of nuclear shell model, right, a mixed kind of potential has been considered. That is a mixture of harmonic oscillator potential and a square well potential. So here they are representing the potential to create a confusion, right? So we have to forget about it. We have to look at the question from here. They are asking about the spin parity and isospin of this state. So this state is 6 carbon 13. Again we have a proton is equal to 6, neutron is equal to 7. So unpaired is a neutron. Again same thing. We are going to write 1s 1p, then again here 1p. So 2 plus 4, 6 plus 1 is 7. So the last neutron is entering in this cell, right? So we have J is equal to 1 by 2 and L is equal to 1. So the spin, spin is 1 by 2, parity is minus 1 power L, because for P we have this SPDF 0, 1, 2, 3. This is L, right? So L is equal to 1. So it means it is a negative. So spin parity is a negative. Now they have also asked about the isospin, right? So as far as isospin is concerned, right, we know very well the last particle is a neutron. This is very important. Now here how we can calculate the isospin, because we have to look that which particle is unpaired. If the unpaired was proton, then we have to write down the isospin of a proton, but here the unpaired is a neutron. We know very well for neutron isospin, right? They are asking about the isospin of unpaired particle, total, not a total isospin. We know very well the total isospin for the nucleon family, 2 members, neutron, proton, right? It is 1 by 2. But for proton, it is 1 by 2, and for neutron, it is minus 1 by 2. So this is the correct answer, right? Spin, parity, and isospin of the nucleus, right? Now, next question. According to nuclear shell model, the respective ground state, again same thing, spin parity values of these 2 nuclei. So in the first case, 8, oxygen 15, means proton 8, neutron 7, right? So again, whatever we have calculated in the earlier case, right? So it will be 1 by 2 negative, because the same thing is there. So 1 by 2 negative for this nuclei, and the second nuclei is 8, oxygen 17. So proton is equal to 8, neutron is equal to 9, right? So if I write down the configuration for neutron, then it will come this one, right? The same way, 1s, 1p, 1p, and then 1d. Last neutron enter here. So spin and parity of these two nuclei is given here. So this is very simple question. We just have to remember the sequence of the configuration, right? I'm going to the next question. Jp of the ground state of a carbon. Again same thing. Jp means spin and a parity. Don't confuse with it. So the same thing, I have calculated it for proton is equal to 6, neutron is equal to 7. So it is 1 by 2 negative. It is calculated in the above example, 1 by 2 negative. So this is the correct answer, right? Now the next is, right, it is the nuclear spin and parity of 20 calcium 40 in the ground state. Now it is a case of even nuclei, right? We know proton is equal to 20, neutron is equal to 20. So we know very well that I have told you there also that even nuclei according to shell model has a zero spin, because all the nucleon are paired. They cancel out one another spin angular momentum as well as orbital angular momentum, and they have a positive parity. So the correct answer is though no need to going into any calculation, 0 positive, right? But we have to remember all the applications of a shell model, only then we can do it. So these were the questions that were asked in GATE exam. So questions were mostly from the shell model and they were very simple, right? If you have the knowledge of the sequence of filling of cells in the nucleus, I mean configuration, right? And the theoretical knowledge that even nuclei have zero spin, even odd even have integral, and odd have a half integral. But for odd we have a formula or rule that we call as Nordim's rules, but it is not used in any question here, but because all the questions were either even odd or odd even nature, right? Well, now I'm starting with the question asked in the NET JRF exam. So you can see here the question. According to shell model, the spin and parity of the two nuclei, right? That is 51 antimony, 125 and 38 cerium 89, right? So we have to first of all note down that which of the nucleon is unpaired. So if I talk about this nuclei, then protons is equal to 51, but the neutrons is equal to 74, because it will make 125 mass number. So you can see here that the unpaired is a proton. So we have to write down the configuration up to 51. Let's look at this nuclei also. So in this case, number of protons is equal to 38, but number of neutrons is equal to again 51, because you can see here. So both these nuclei have 51 configuration up to 51, and in the first case the unpaired is proton, whereas in the second case the unpaired is a neutron. But the thing is that both neutron and protons are filled up to configuration 51. So we have to write down the configuration up to 51. So we know very well the sequence is 1s, 1p, 1d, right? 2s come in between, right? Then 1s, 1p, I'm writing here 1s, 1p, 1d, 2, 1s, 1s, 1p, 1d, 2s, 1f, 2p, 1g, right? In this case, so 1s, it is here, right? 1p, 2 cells, 1d, 2 cells, but 2s comes in between. Here they are not considering, the value of n, so writing it at n only, so it is basically 2s. So it comes between these two cells. So then this one 1d, and then 2s in between, then we have 1f. You can see here 1f. I have also told you that in case of 1f, the 2p comes in between. Right? I mean 2p 3 by 2 comes between these two cells, and then 1g is the next. Right? You can see here. So the configuration is 1s 1 by 2, 1s 1p 1d, right, 2s 1f, right, then 2p, right, then 1f, right. In this way we can write down the configuration, and we can see that the last nucleon is going in a cell, this one, 1g 7 by 2. The thing that we have to remember, I told you in that lecture also, that what is the, which of the cells make the intersection between the other cells. So these were the first one was 2s, right, that is here. Then we have 2p, right, that comes between these here, between 1f, right, 1f cells. Then 1g as it is, right, 1g have no issue. Then up to this configuration, and then in the higher configurations also, up to I think 80 there is no issue, we can write down directly, but up to 51 it is enough. We have to remember, I told you that the configuration up to 50, right, and we have to remember up to 52 things, right. One is the sequence, and the other is that 2s will come in between these two, 2p will come between the f, right, that is 1f 7 by 2 and 1f 5 by 2, right. So 2p 3 by 2 will come here, and 2p 1 by 2 will come here, right, between the 1f, right, then 1g, right, it is here. So you can see here now the value of j is 7 by 2, right, and value of L is equal to 4. S, P, D, F, 0, 1, 2, 3, and then S, P, D, F, G, then 4. So L is 4. So you can see here the spin and parity is 7 by 2 positive. So same will be for this nuclei, because it doesn't matter whether it is proton or neutron, that is unpaired. The configuration structure is same. So same thing again here. So again same spin and parity, and the correct answer is D, right. So we were asked here to find the spin and parity of two nuclei, right. These are given here, and we have calculated the spin and parity, right. These two nuclei were actually, this is antimony, I told you, and it was strontium. I think I called it as cerium, so that was wrong. Sorry for it. It is strontium 38 and mass number 89, and it is antimony, right? So we calculated the spin and parity of these two. Now I am going further. The next question. Now the question is related to the semi-empirical mass formula. The binding energy of a light nucleus in mega electron volt is given by the approximate formula, this one, right? Where n is equal to a minus z, we know very well is the neutron number, the value of the z for the most stable isobar of a given A, right? Now here we are given the formula. It is volume energy term, surface energy term, Coulomb energy term, symmetry energy term, and the pairing energy term is taken as 0. It means the nucleus is having even odd or odd even structure, because for them the pairing energy term is equal to 0. For even it is positive, for odd it is negative, right? So now the first and foremost thing is we have to put here n is equal to a minus z, so it will become plus 30 divided by a into a minus 2z whole square. So now we know very well that what is the formula for the most stable isobar and how we have to calculate it. right? So if we want to calculate this result, then we have to take the differentiation of this with respect to z by taking a as a constant. It is written here curly v upon curly z at z is equal to z dash, provided a is equal to constant should be equal to 0, right? We have derived that relation, not derived, but I have told you that relation in the earlier lecture also, the condition for the most stable isobar. But here you are already given the mass formula. So simply what I have to do, I have to take curly v upon curly z by keeping in mind that the a is constant. So when I will take curly v upon curly z, right, what will happen? Let me expand it further so that calculations can be done quite easily. So when I will take the differentiation, right, it will become the first term, it is 0, second term 0, both are constant, minus 3y4 into 2z a power minus 1 by 3, right, plus 30 divided by a into a minus 2z square. So it will become a minus 2z, right, into it will become 2 because differentiation will be into 2 this one into differentiation of this is minus 2, right. So now we can simplify it further. So when I will simplify it, it will become, you will get minus 3y2 z a power minus 1 by 3 plus 30 into 2, 60. Now it will become first of all minus, right, because we have minus here. So 30 into 2, 60 into 2, 120, right, divided by a into a minus 2z, right. So what is the next step? The next step is to multiply with the a here. So then what I will get? I will get, when I will multiply, minus 3 into z a power 2 by 3, right, divided by 2 minus 120, right, into a minus 2z is equal to 0, because I take a as common, multiply here, right, and then I equated it equal to 0, right. Now 2, so I am also taking 2 as LCM, multiplying here, so it will become, in the next step I can write minus 3z into a power 2 by 3, right, minus 240 into a minus 2z, right. Space is limited, so I have to use, I can use it here, I'm writing it here. So it will become, I'm writing it here, minus 3z a power 2 by 3 minus 240 into a minus 2z, right, is equal to 0. Now 3 is common, so it will become z minus z into a power 2 by 3. So it is 80 into a minus 2z is equal to 0. So then after, in the next step, what I will do, I will open the bracket, minus 80 into a into plus 80 into 2, 160 into z is equal to 0. The rest of the things, this will remain as it is, right. So in the next step, what I will get, I am doing it here, it will become minus z a power 2 by 3, right, minus 80 a plus 160 z is equal to 0. So I can take z as common, z common into 160, right, minus a power 2 by 3 is equal to 80 a, right. So now if I took this toward this side, I will give, it will give me z is equal to 80 a divided by 160 minus a power 2 by 3. I take 160 as common, right, what I will get, Z is equal to 80A divided by 160 into 1 minus A divided by A by power 2 by 3 divided by 160, right? 82. So it will become A by 2 into, I took it upside, so 1 minus A power 2 by 3 divided by 160 whole power minus 1. So you can see here, this is the correct answer. A by 2, 1 minus A power 2 by 3 divided by this is the correct answer, right? So this is the way of solving this question. You can see A by 2 into 1 minus A power 2 by 3 divided by 160 power minus 1. So my answer is same. A by 2, 1 minus A power 2 by 3 divided by 160. So what I did, I simply took the differentiation of this expression while keeping in mind that A is constant and Z is equal to Z naught, you can say, and then I equated that differentiation equal to 0. Curly V upon curly Z is equal to 0. So I got this expression. So this is the answer to this question, right? Now the next question is a spin half particle A undergoes a decay by this rule. Means the spin of A is, you can say, 1 by 2, where it is known that the B and C also have spin. Means this also, I am writing it here, A is equal to B plus C plus D, right? A spin 1 by 2, B spin 1 by 2, C spin 1 by 2. So D spin is unknown, right? So I can calculate the spin. So this was the question I was talking about. You can see here. The spin half particle A, I have written here, A is equal to B plus C plus D. The spin of A is 1 by 2, B and spin C spin 1 by 2, 1 by 2. So they are asking that the allowed value of the spin of the particle D, what can be, right? Now, we know very well that the spin of the left hand side particle is 1 by 2. So the spin only will be conserved if the spin of the right hand side is also equal to 1 by 2, right? And it will be 1 by 2 only either these two spins add up, they will give spin 1, right? 1 by 2 plus 1 by 2, 1, and then minus 1 by 2. Means the spin of the D particle is 1 by 2, right? One possibility, right? Second possibility, these two spins are, anti-parallel. 1 by 2 minus 1 by 2, 0, and in that case the spin of the D particle is 1 by 2. So the only possibility that is given here in all these possibilities is C, that consider only 1 by 2 only, right? So the spin of the D particle will be 1 by 2. So this is the correct answer, because the other values of 0, 1, 5 by 2, they are not, allowed by the conservation of spin angular momentum, right? I explained it that the spin of the left hand side and right hand side should be equal to. So if I look at the spin of the different particles, the only allowed value of the D is spin half particle, right? It can have two orientations plus minus, but it is only 1 by 2. Allowed value is 1 by 2. So this is this was the next question. I'm going to the next question now. Now, according to the shell model, the total angular momentum in units and parity, I mean spin angular momentum and parity, again the same kind of question. Number of protons is equal to 3 and number of neutrons is equal to 4, right? So the unpaired is proton, so we have to write 1s 1p, 1s2, 1p 1. So the last nucleon, that is proton, goes to the, let me change the color, otherwise maybe not visible properly. So J is 3 by 2 and L is 1. So I can write the parity as negative and the spin as 3 by 2. So the correct answer is 3 by 2 with negative parity, right? Find it. It was very simple question, right? I'm going to the next question. You can see here the winding energy. Again, the question is from semi-empirical mass formula. The binding energy of a nucleus with mass number A and charge Z is given as this volume energy term. surface energy term, symmetry energy term, and this is a Coulomb energy term, right? Values are already given here, right? The most stable isobar for the nucleus with A is equal to this. Now what we have to do? I did it, earlier question, that curly V upon curly Z should be equal to 0 provided A is a constant, right? So we will differentiate this equation, right? So here you can see the differentiation. Now when we are taking the differentiation, this will become 0, this will become 0, both are constant. We will have only differentiation of these two terms. So the differentiation is given here, right? For the first term, again, it was a, you are given here, right? 2z minus a whole square. So it will become 2 into 2z minus a, right? 2 into 2z minus a into a differentiation of these two, right? So then in this question, they have put the value of, we know very well, n is equal to a minus z, right? So they have put it here and written in earlier case that I have discussed in the previous numerical, I took it as a minus 2z, right? So there is nothing wrong. They have put the value of z instead, right? So when we will put the value of z or a, then you can change this in this way, but you will get the same result, right? So it will become this divided by a, right? Here you can see here a, right? Then when you will take the differentiation, 2z ac upon a by 3, 2z ac upon a by 3. Now it should be equal to 0. So the next thing is to put the value of z, not z but a, right? And value of a symmetry energy term and Coulomb energy term. So these are given here, right? Symmetry energy term, Coulomb energy term. So you can put and simplify this and you will find the value 82.3, right? This is the value of the Z for the most stable isobar, right? 82, right? 84, sorry, yes. No, but the calculated value is 80. We have found it 82.3. So we have to look at the nearest value. So in this, options, the nearest value is 84. So we can say, because all these, value that we put here, they were, approximations. So we can say that the nearest value in these options is 84, right? Now I am going to the next question. It is again of the nuclei of mass number A is equal to 125, the binding energy calculated from the liquid drop model, that is semi-empirical mass formula they are talking about, the value of the Coulomb and symmetry energy are given here, right? Now I have wrote the formula in a previous lecture for calculating the value of Z for most stable isobar, and the formula was Z is equal to 2 A symmetry A divided by A Coulomb energy A power 2 by 3 plus 4 into A symmetry energy. This was the formula that I have written in that lecture. Now I can use this formula for calculating this value. So what I have to do, I have to put all the values here. So 2A symmetry, symmetry 2 into 22.5 into A means it is 125 divided by A Coulomb energy 0.7 into A power 2 by 3. A power 2 by 3, I can write A upon A power 1 by 3, that is 125, and 125 power 1 by 3, 5, 25, it will give me 25, right? Plus 4 into symmetry 22.5. So when I will simplify it, I will get in the next step this into this 45 into 125 divided by when I will multiply it, I will get 25 into 17, 17.5 plus 22.5 into 4, that give me 90. So when I will simplify it, 45 multiplied by 125 divided by 107.5. So when I will simplify it, I will get 52.32. You can calculate it. So 52 point means the nearest value is 52. So here 52 is already given, right? So this is the correct answer. So this is the most stable isobar, right? They have actually asked of the nuclei of the mass number, the binding energy calculated from the liquid drop model, right, will be maximum. Maximum means again the condition of maxima, and we have the formula that most stable isobar. The thing is same, but the way of asking is different, right? So this is the question again from the semi-empirical mass formula. Now I am going to the next question, right? You can see here, let ES denote the contribution of surface energy per nucleon in the liquid drop model. Then the ratio of ES for these two nuclei. We know surface energy Bs is equal to A surface energy into A power 2 by 3. But that's saying ES is equal to Bs upon A per nucleon. So divided by A. So when you will divide, you will get Bs upon A, that will give you As into A power minus 1 by 3. So you can say Es is directly proportional to A power minus 1 by 3. So they are asking the ratio Es of aluminium and Es of zinc. So you can see here, right? So you can calculate it by simply putting the values, you will get 4 by 3, right? This is the way of calculating this question, right? 27 power minus 1 by 3, 64 power minus 1 by 3, right? You will get 4 here and 3 will come down because you will get 3 here and 4 here, but they will get inverted because the powers are negative. So 4 by 3 is the correct answer, right? Well, now I am going to the next question. The question is, according to Shell model, the nuclear magnetic moment of 13 aluminium 27 nucleuses, you are given the value ZL, ZS for both neutron and proton. So this question is based on the application of Shell model for calculating the magnetic dipole moment of the nuclei. I have explained in the early lecture that according to Shell model, only those nuclei possess magnetic dipole moment which have even odd or odd even structure or odd structure. Even nuclei don't possess magnetic dipole moment, right? And it is also known that the magnetic dipole moment of the nucleus is because of the unpaired nucleon. So first of all, we will look that which of the nucleon is unpaired. So here we have a proton is equal to 13, neutron is equal to 14. So unpaired is a proton. It means we are going to use the value for a proton, that is ZL is equal to 1 and ZS is equal to this. These will not be used, right? Now the next thing is we have to calculate the spin also, because only then we can proceed further. So for calculating spin, I have to write down the configuration. So 1s, 1p, 1d, right? 2, 4 to 6 to 8 plus 5, 13. So the last nucleons goes into this cell, and for it spin is equal to 5 by 2. We can even calculate the parity, but it is not required. Now I am writing the formula for magnetic dipole moment. Mu L is equal to 1 by 2 GS plus, right, I minus 1 by 2 into ZL whole term multiplied by nuclear magneton, right? Here GS is spin G factor and ZL is orbital G factor, right? And this formula is used for calculating the magnetic dipole moment when we have I is equal to or we can say J is equal to L plus S or L plus 1 by 2. So you can see here that I is equal to 5 by 2. 5 by 2 means it is 2 plus 1 by 2. the next term will be 1D 3/2. So it is actually L plus S. So that's why I'm writing this formula. Now what is the next thing? I have to put the value of all terms. So if I put the value, then I will get 1/2 into GS means you can see here 5.586 plus I means 5/2 minus 1/2. So 5/2 minus 1/2 it is 2, right? Into ZL, and ZL is equal to 1 for a proton. So no need to worry. So into multiplied by whole term mu n, nuclear over magneton. So if I simplify it further, what I will get, let's use this space, it will become 5.586 plus 4 divided by 2 into mu n. So it will become 9.586 divided by 4, right? Sorry, 2 mu n. So when I will simplify it, 4, 7, 9 and 3 mu n. So and positive sign also there, 4.793. So C is the correct answer, nuclear over magneton. So you see how I calculated the magnetic dipole moment by taking into consideration the formula that is given here, and this formula is used when I or J is equal to L plus S, or you can say L plus 1/2. If it is L minus 1/2, then we have other formula than that I have discussed in the earlier lecture, right? So this is the next. This was the next question. Now I am going to the next question. The question is again from the shell model. The spin parity assignment of the ground and first excited state of the isotope this 28 nickel 57. So proton is equal to 28, neutron is equal to 29. So unpaired is a neutron. One thing is there. So configuration, same thing. I am not repeating it again and again. It is clear that the last neutron is going in this cell. So J is equal to 3/2 and L is equal to 1. So parity is minus 1 power 1 negative. So the ground state spin and parity is a ground state, this one. Now what about the excited state, first excited state? First means the immediate next cell to this, right? So 1s, 1p, 1d, 2s, right? 2p, then we will have the next cell, you can see here, it will become 1f5/2, right? You have to remember 1s, 1p, 1d, 2s, 1f, 2p. So 1f is the next one, right? That comes here, 1f7/2, and then we will get 1f5/2, right? 1s, 1p, 1d, 2s, 1f, 2p, sorry, right? That's why p is here. I told you that p comes in between the two subcells of f, right? So it is the next one. So the next one, f, for f, spin is 5/2 and parity L is equal to 3, again negative. So this is the way of calculating the spin and parity of the first excited state. We have to look at the immediate next cell in which the nucleon is present, and for that we have to remember this sequence. This was the last question of this discussion. So in this entire discussion, I talk about the different questions that were asked in different exams, based on the cell model and semi-empirical mass formula, right? So thank you very much.